Welcome to the course on two-dimensional signal processing, principles and practices. As we are doing this 2D signals and the continuation of the 2D signals, we would look at the exponential functions today. And the 1D exponential function, we had already discussed that x of n is equal to e power sigma plus j omega n, or it could be written like a alpha n, alpha equal to e power sigma plus j omega. So in this 1D function, how does it look like how do we get this plot of the one? So if you plot this x of n only having a signal a of n, or any of the value a, it could be of 0.8 or any of this, just alpha n only, where alpha is going to be a real value, that is 0.8. So if we plotted x of n is because this is a is less than 1, it is going to be a decaying function when we plot with respect to n. So the 1D exponential function looks like that. And if we have this complex also taken into account, say e equal to sigma plus j omega, where this can be written as e power sigma plus j omega is going to be sigma plus e power sigma, and this is e power j omega. So e power j omega can be written like cos omega plus j sin omega. So if you multiply this by n, anyway this n would be here. So considering this sigma value 0.6 and omega is 2, and taking only the real part of it, here cos omega n is plotted. So you have the decaying exponential with the frequency of the signal would be omega, what is here 2. So this will have this sign both positive and negative, and that omega frequency, that cos omega n is influenced by the decaying function on its amplitude. So it would decay, as well as it's not sustained oscillation, now it is a decaying function. So the exponential decaying functions look like that in 1D. So how do we express this in the 2D cases? So 2D exponential sequences are represented as x of n1 comma n2, where this equal to a power n1 and b power n2. So this a and b can be of any constants here. So these two independent variables n1 and n2 having this 1 on a power n1 and b power n2. So the product of this can be expressed as two 1D exponentials. If this is the system for the case of analysis, this type is very important to know. And how do we plot this exponentials? We'll see that in the next slide. That is when 2D signal is x of n1 comma n2, it's equal to a power n1 and b power n2, where a is 0.5 and b is 1. So in that case, a is less than 1 anyway to them, and b is 1 only. So how do we get this exponential in 2D? So let's see that n1 is this here and n2 is in the y-axis, x and y-axis. If n1 equal to 0 and n2 equal to 0, so this would contribute as 1. So that's the point in which we get 1. And if n1 is again 1 and n2 is 0, so this would be a, so the next point, and then n1 is 2, and this is going to be x a2, and when n2 is 0, similarly n2 is 0 and when n1 equal to 3, so this is a square a3, you get these points. And when n2 equal to having the values and n1 is becoming 0, so 0 0 and n2 is 1, so this point is simply b, and b square in this case, and b cube here, and then a and b we have 1 and 1, so this would be ab. And if this is 1 again and this is 2, so you get a square ab square, and similarly here a square b and a cube b and so on. So here we would get, if it is n1 and n2 are 3, a cube and b cube, these points we would get. So the exponential sequence cannot be viewed in the 2D like decaying one, but the values, according to the values, it would be exponentially decaying. But if we view that in 3D, that n1 and n2, you can see that it is the surface which is decaying like the 1D exponential. So this is just a representation of an 2D exponential in 3D view with respect to this x of n1 comma n2 is depending on n1 and n2 values. This is plotted for a and b of 0.5 and 1. This could be varied, and we can get also. We will see another example in which this is 4a in a power n1 and b power n2. In this 4 a constant is multiplied. How this a is 0.8 and b is 1 here. So if we plot this sequence again, how do we visualize it? Or in the 2D, the exponential sequence still, that is you cannot have that decaying can be seen, that n1 equal to 0, n2 equal to 0, this becomes 1. So you get the origin as 4, and when it is 1 and it is 0, so it's going to be 4a, and next one it will be 4a square, and n2 is 0 and n1 is 2, and n1 is 3 and n2 is 0 again, 4a cube. So similarly in the y axis, when n2 has some values and n1 is 0, so we get this one 4b square, 4b cube, then both exist, n1 and n2 1, then it will be 4ab, and similarly in this here 4a square b is for 3 and 3 values, 4a cube and b cube. So this would continue here. There is no restriction on the value of n2 and n1. So this sequence looks like that. So this is just how to sketch this 2D signals, that exponential sequences we had seen. So if you visualize this again, you can clearly see that this exponential decaying sequences here, this has a 4 value here. When b is 1 value, this is the value which is the y-axis it shows, and the a values are shown over here. So this is going to 4a and a square and a cube. This scale represents, and here this. So you can see the exponential decay over here, and this can be visualized in 3D. Now coming to the periodicity of the 2D sequences, we have learned the 1D periodicity as x of n equal to x of n plus n. So a signal is said to be periodic, it has a fundamental period, and when this x of n equal to x of n plus 1, that n is the fundamental period. So the n is a finite integer here, small n. If we extend this idea of to the 2D, so it's like x2D sequence, x of n1 comma n2 is said to be row wise periodic or column wise periodic in case of 2D. So it's not in the case like the 1D, in 2D we define this as row wise or column wise periodic. So if it is row wise periodic, what is the condition it should be obeying? So if x of n1 comma n2, the 2D signal should be equal to x of n1 plus p, instead of this n we have here plus p comma n2. N2 doesn't, it's not the periodic, whereas n1 is having the fundamental period p. So p is an integer, that is the integer period of a sequence. And then if it is column wise periodic, so there are two types of periodicity in the two-dimensional signals. The column wise periodic, in the sense x of n1 comma n2 is equal to x of n1 comma n2 plus q. So this q is the fundamental period for column wise periodic. So if both wise, row wise and column wise, your signal is periodic, then it is x of, take this case, if both wise, that is row wise and column wise periodic, then it would be x of n1 plus p comma n2 plus q. So in that case it is periodic in both ways. So in these cases, row wise the fundamental period is p, and column wise the fundamental period is q. So both are integers here. These are the period of the sequence. So let us visualize that how this x of n1 plus p comma n2, that is row wise periodic, appear. I mean in 2D signal, n1 is this and n2, there are some samples which is shown with different shapes for distinguishing the data samples. So suppose this is one value and this is another value and so on, 0, 0, 0, 1, 1, 0, 0, 1 here, this is 1, 0, 2, 0 and so on. So if in row you can observe a pattern here, that is these two are one set of values which is repeating over the row. You can see this. This is called these two samples here, even it goes from this side, even in negative index of n1 and here as well, and this would continue from minus infinity to plus infinity for row wise periodic. These two samples are keep on repeating, that for then n equal to here 2, and this is also valid for other rows over here, that is these two samples, that is different two data values are same, I mean repeating in another row. And similarly here the third row which is having the two samples, similarly these two samples are repeating over that row. So this every row has the periodicity here. The periodicity now it's obvious, it is because two samples are getting repeated, it's p equal to 2 in this case. So, but every row if you take, these are different values here. This value is not same as this is not same, and here these are different, so the symbols shown are also different here. So, periodicity can be the row wise periodicity can be visualized clearly in this picture. Now, if we take the column wise periodic, so how does this column wise periodic appear? So, N1 and N2, in which this is one column given and this is another column given. Similarly, the third column also we can have the 4 column each, any data. So, in this, what is the periodicity we observe? So, if we take this 3 samples, 1, 2, 3, and this 3 again appears here. Okay, so this 3. So, this is column wise periodic. So, whatever the length of the column, that 3 or 2 samples, the periodicity would appear. So, Q equal to 3 here, the N2 plus Q, and similar thing can be observed in the other column also. You can see that is 3 different samples than the first column is appearing again, and in that column. So, it is every column will have the repetition. That is the column wise periodic. If you recall in the 1D signal, the pattern is getting repeated in N. Okay, so similarly here this is with respect to N1 it would be repeating, or with respect to N2 it would be repeating. So, if it is repeating with respect to N1, that is the row wise, in the row it is repeating, that is called the row wise periodic. If the column it is repeating in this case, that is going to be the column wise periodic. So, if we combine, this Q is here because 3 samples are repeating here, the pattern of 3 gets repeated. So, Q equal to 3. Now, if we combine these 3 or the 2 of them, Q equal to 3 and Q equal to 2, or P equal to 2 or P equal to 3. So, any of this PQ can be combined, 2 or 2 3 3 2 combinations, this row wise and column wise can be set, and it is also separable, that is periodic separable, if that x of N1 comma N2 is row wise periodic, which is also equal to column wise periodic, and that is also equal to row wise and column wise both periodic, where P and Q are integers here, and for all N1 and N2 values. Then this sequence x of N1 comma N2 is separable, that is periodic separable. So, that we would see some example, but we would like to plot the sequence x of N1 plus P comma N2 plus Q. So, this pair P and Q is called the periodic or the period of the sequence. Now, if we take the example in which you can see this 2 is repeating over here, that is row wise N1 plus P here, and then if we can also see that this 2, that is N2 plus Q, is repeating over here. Okay, so this is column wise. So, this is valid for every column and every row. So, this row if you take this 2 are repeating, and if you take this column, this 2 and this 2 are repeating again. So, it is the P and Q are 2 here, P equal to 2 and Q equal to 2. So, the periodicity is 2 by 2. Okay, if it is only 1, then it is P is 2, and similarly in column wise Q is 2. So, if you combine both this row wise and column wise, this would appear in this fashion. So, now sketch this some of the sequences. So, it is a first thing you need to visualize the 2D sequences, and how do we plot it, and we will get familiarized with that, so that it can be used in the future analysis. So, x of N1 comma N2, it is equal to, now given as 2 delta of N1 minus 1 and N2 minus 1. You can see the shift, right shift in N1 and N2, and the same impulse is given N1 minus N2. So, this is a diagonal impulse. So, the N1 minus N2. So, we have seen both that now the del of N1 comma N2 is the signal, it is a 2D impulse, and if you shift it one sample in both the directions and multiply by 2. So, what is the sequence we get here? So, this is N1 shifting here and N2 shifting here. This is the N1 comma N2 at this point, this is 1, and but the magnitude is here 2, that is amplitude here given is 2. So, the sequence del 2 of del of N1 minus 1 N2 minus 1 is 2 here. So, the 2 is represented in the bracket, and if we plot this sequence N1 minus N2 equal to 0, so that means N1 equal to N2. So, whenever N1 is and N2 equal, this would result in 1. So, this impulse would result in 1. So, we have already seen this diagonal impulse. So, in which these are all values 1, but n1 and n2 both are equal. When it is positive, n1 is 1, n2 is also 1, and similarly in this case. So when we take the negative indices n1 minus 1 and n2 minus 1, n1 minus 2, n2 minus 2, and similarly n1 minus 3 and n2 minus 3. So this is a diagonal impulse. So this now this x of n1 n2 contains these two components. By adding the two, so what would be the resultant? So if we take the other points of this, here where here 0 0 minus 1 minus 1 minus 2 minus 2 minus 3 and so on, these values, this first component doesn't have any values, that's 0. So if you add, and similarly the other, apart from the first one, it has all values 0 here. So if you add these two, so you'll get at this point 3. Okay, and then here you have the value 1 plus 0, 1 plus 0, 1 plus 0 here, this is another one, and here these are all ones, these values are ones, and only here you will get 3. So the amplitude difference or the value of the sample can be only represented this way in this. It is so if you simply put a dot in 2D, that doesn't mean anything related to the amplitude. You need to mention what is the amplitude. So the default values can be taken as 1, but still this amplitude needs to be specified when we put the dots here. This is 1, and this sample is going to be 3 here. This is the signal which we got through this example. And we also plot a sequence. X of n1 comma n2 is u2d, that is representation here t or two-dimensional, anything would work, n1 minus n2. So now this component n1 minus n2, if we have, how does this signal look like? So whenever this is greater than or equal to 0, this step sequence u is, of course, it's a standard notation for the step sequence. So this is a 2D step sequence. When n1 minus n2 is greater than or equal to 0, this values would take 1. So unity for n1 minus n2 greater than or equal to 0. So in that case, how does the sequence would be? N1 and n2. Here you can see that n1 and n2 values, if it is equal, also this unit step will have one value. So these are all values 1. So n equal to n1 equal to 0 and n2 equal to 0, n1 equal to 1 and n2 equal to 1, and these values here. And similarly this similar this fashion, this diagonal will all everything is 1 now. And what about these conditions? Here if you take, suppose this value n1 is 1 and n2 is 0, so n1 is greater than n2, so this is valid. And the over here similarly, if you take any point here, n1 is 1 and n2 is minus 1, so that is also here valid. This n1 is greater than n2, so this is 1, all of them, all the values are 1. So it takes this shape that as a wedge. Here it is for this diagonal of like impulse greater than all the values, this is going to be 1. So this would extend up to n1 infinity and similarly n2 infinity here, but in this values this is 0. So this the values less than the diagonal, so all of them would be 0 in this portion, and this is 1. So the step sequence which is having the diagonal like line impulse like 1, but this is a step sequence which can be plotted in this fashion, in this way we can visualize this. It's a shape which is used in the 2D signals. This is one example of the 2D step sequence. Can we combine these step sequences with shifting and scaling operations? So right now we'll use the scaling, we'll hold it for a while, but we can use the step with the shifting. Okay, so in the x of n1 comma n2, this u is a step sequence 2n minus n1 and 2 minus n2. So this is just a flipping and shifting. Okay, so this is again the step sequence, this u of n1 plus n2 and n2 plus 1 here. So in this case, how do we plot this? This is a product of two sequences. So first we will plot this sequence here. You can see even plotting this, it's not a straightforward u of n1 comma n2. So as we have learnt in the signal operations, you can shift it and then do the scaling. Here it is the other way we have done here. This is minus n1 minus n2, that means flipping the sequence first. The flipping minus n1 minus n2, u of n1 comma n2 is a first quadrant sequence where n1 and n2 greater than or equal to 0. U of n1 comma n2 exists. That's 2D step sequence. But minus n1 and minus n2, the first quadrant is flipped, is a mirror image. Here it would appear in the third quadrant. So all the signals u of n1 comma n2, so this is n1 and this is n2. So the sequence of step sequence here, u of n1 comma n2 is flipped now, and you can see that flipping is in the third quadrant. Now after flipping, we have to add this n1 plus 2 and n2 plus 2 here. So that would, n1 would shift again here. If we do that shifting, you can see that shift, n1 shift to 2, and this also would shift to 2, that is plus 2. So we have the sequence from here, and after this it is 0. So I mean below 2 are the 2, 3, 4, 5, it is 0, again 3, 4, 5 and all, it is 0. So but the sequence exists in this region from 2 comma 2 to infinity in all other directions. So this is the sequence which we get it from the first component. The step sequence, can visualize it now in the 2D. And what about this u of n1 plus n1 and n2 plus 1? So here n1 plus 1 and n2 plus 1, the sequence is plus 1 and plus 1. So n1 plus, you move it in this way, that is in the advancing, and here also n2 is advanced here, one sample. So the step is now, instead of having in this portion, so we have this one only in the case of u of n1 comma n2, and this is shifted now, this plus 1 and plus 1, moving this shape to this here. So now this is the sequence which is representing u of n1 plus n2 shifted. Here if you multiply the 2 minus n1, 2 minus n2, that is having the sequence, this is 2 comma 2, and this is also existing in this region. So we get a sequence which is the product of this 2. So you have only 1, so from this onward exist only this portion, that is 1 comma 1 minus 1 here. So from this is the one which is common between the 2. So this value and this values are existing in this case up to this point only, though it is having values above it, but this signal is only up to here. So we have only the sequence we get is x of n1 comma n2 is this. Okay. So this is the plot of shifted sequence and product of 2 sequences. Now we come to the finding the response of a system in terms of the convolution. So if we know the impulse response of a system, taking any input and convolving it would give the response of that system for this particular input. So what is the process in which we do this convolution operation? So we know the equation, that is y of n equal to k varying from minus infinity to plus infinity, x of k h of n minus k. This now first given x of n is this, suppose 0.7 n u of n, and the h of n is 0.2 per n u of n. So now change this to base to k, x of k and h of k, and then flip this k to negative, that is make the mirror image h of minus k, find it, and then shift this h of minus k by adding n to it, h of minus k plus n, and depends on the n value for which this signal exists, and then multiply, and the common area, common values if we have, then the summation is valid. Out of the range of these signals, that summation is not valid. So now if we take this, change this to x of k, that is the base to xk, that is 0.7 k u of k, and the h of n minus k is this. We can first change it to h of k, and then find the flipping h of minus k, and then add plus n to it, or the straight away this is h of n minus k equal to 0.2, where n is replaced with n minus k, and this also u of n minus k. So if these Signals are causal because it is multiplied. Here you can see that u of n and u of n multiplied. So, the signal exists only n greater than or equal to 0. This is 1D. This similar convolution sum we'll see in the 2D as well. So, the y of n, this equation, now if you're substituting in this equation x of k, this is 1, and h of n minus k is this, and finding u of n minus k is valid for what are the values of it. So, n is greater than or equal to 0, then this function, it is because this definitely k greater than equal to 0 only, this will become 1. So, 0.7 k, that is power k here, 0.2 n minus k. So, this is valid for n greater than or equal to 0. So, for n less than 0, this summation would give the 0. So, using this, you can 0.2 n is not under the summation, 0.2 power n is not under the summation. So, we can take this out and take the common one here, 0.7 by 0.2 k u of n and 0.2 power n. So, we get the a power k is varying from 0 to n. So, a power n. So, this gives the closed form solution as 1 minus a power, this is finite. So, n plus 1 here, 1 minus a power n plus 1 by 1 minus a is this 0.7 by 0.2, and this 0.2 n. So, this can be simplified further to get the y of n equation, and of course, this is valid for with n greater than or equal to 0. So, that is why it is the multiplier. So, this is the summation. Now, this is the analytically you can say this is the convolved sum or the response of this system. If it is, then x of n is that particular x of n what we had given as an input, and h of n was the impulse response, and this y of n is the system response. So, here we are taking the two signals and convolving them, the resultant sequence would be this. If you plot it y of n, you get. So, we will see the plotting also, and we will see the graphical visualization of the operation which we had done. So, k first convert that x and change this to k base, x of k 0.7 power k, and then this is varying exponentially decaying, this is less than 1. So, it is going to be decaying, and h of k find it 0.2 power k, and similarly change the base also n to a k here. After that, flip the sequence h of minus k. So, this is the sequence which is on the right hand side is now flipped to the left hand side in 1D, and shift it n minus k plus n. So, whatever this n value can be, n can be less than 0 or n can be greater than 0. So, accordingly this h of n minus k would be, and we would be by shifting it, by shifting plus n and finding the common area between this x of k and h of n minus k, and sum the values that would result in the. So, this x of k and h of n minus k. So, we would find out the values, this for n greater than or equal to 0. So, this would be h of n minus k would extend up to this point. When n is less than 0, h of n minus k would be in this here. So, you do not have the common area here. You can see that is why it results in say 0 the summation, whereas here this has a common value. So, multiply this common indices which the signal exists and find y of n. So, in this y of n is going to be 0 from 0 to n in infinity. So, you get a sequence y of n through the graphical convolution as well. This is just a visualization of the process which we had done in the this is related to the 1D. And if we have the finite sequence, the previous one was an infinite sequence, though it is from available from n equal to 0 to infinity because of u of n. We have the minus infinity to plus infinity sequences. So, you have to deal with either the graphical sequence or the analytical way, but when we have the finite sequence, this is known that only 4 samples, 5 samples are existing, then how do you make this convolution? So, this knowledge would help in finding the 2D convolution as well. So, the equation is y of n, we can straight away substitute this xn and x1 and x2. So, here x and h we have given, we can take this as xn and the another signal as h of n. So, we would either substitute it here, x of k, and this signal is at point 0, n equal to 0, 1, 2, 3. Let us take this fashion 0, 1, 2, 3. The signal can exist in negative indices as well. So, then we can accordingly deal with the convolution sums. In this case, if you take one signal, it is 1, 2, 3, 4, which is given h of n, this is h of n, and then another one 2, 1, 2, 1, this is x of n. Okay, and then multiply each row, this 2 with 1, 2, 2, these are the value 2, 3, 6 and 2, 4, 8. Similarly, the second row 1, 2 and 3 and 1 4. So 2 1 2 4 6 8. The third row would be 1 1 2 3 4. So now how do we get the after multiplication? This is shift and multiply operation. So we take a cross, draw the cross lines in this way fashion and take this value. This is y of 0. And if you compute it with x and h shifting operation, you would get the same thing 2. And in the second row, like this cross 1 plus 4, it would be 5 here, that is y of 1. This is y of 0, y of 1, and the next row is y of 2, which is yielding 2 plus 2 plus 6, this is 10, and the other one is 16. Okay, so here 7 plus 8 15 and 16, and the next one is 12, and this is 11 and 4. So we would get this 12 11 and 4 6. So what is the response we get it from here? That is from here, this is y of n equal to 2 5 10 16 12 14 11 and 4. How many samples we got it from here? That is 3 plus 6 plus 1 7, whereas the original length of x1 and x2 were 4. x1 as 4 and x2 as 4, or this is x and h, which is having 4 and 4 samples. So the resultant convolved sequence in a linear convolution has the length n1 plus n2 minus 1, that is 4 plus 4 8 minus 1. We have 7 would be the sample length. So we get this here because it starts with the 0 index. So here 2 5, this is 0, we get this. This is for the finite sequence. So we can also do it for the indices negative in a similar fashion, and you have to identify where the 0 using these methods. This is for the convolution sum. So we have done the 2D signals plotting in this lecture. That is what we had learned to the step sequence and the impulse sequences. We used that step and impulse sequences by shifting and adding them or getting the product of two sequences. And how do we visualize that in 2D? So when we get the that's what we have 3 examples we did. Apart from that, we had also seen the exponential signals. In the exponential signals, how this we cannot see the exponentially decaying function as in 1D, but the values of in 2D case. If you plot it in 3D, yes, you will be able to visualize that signal is decaying, the amplitude decaying, and nature can be visualized. So we have seen the exponential sequence and the impulse and step sequences. To how do we, and in 2D step sequence itself, it's not how do we get the wedge shape, and then we also make the addition and summation of these sequences, and 1D convolution sum we have done in this course. Thank you.